All right, Jam, I'm going to paint a picture for you.
Literally?
No,
Okay.
with my words, which is a picture's worth 1,000 words, but I will use less than 1,000 words to paint this picture.
Okay.
So imagine it's super cold outside.
Like it was?
Like it was.
Not too long ago?
Not too long ago. Like below freezing.
Okay.
In the teens.
Okay.
In the Fahrenheit teens. Okay. Celsius in the negatives.
Okay.
And you go out to your car and you start it up and you drive away.
Mm-hmm.
And as you're driving, every bit of water that you see is frozen.
Yes.
But somehow the gasoline in your car is not frozen.
Ah.
Have you ever wondered how that is?
I guess, to be honest, I have not. But I guess, are we sure it's not frozen?
We're pretty sure it's not frozen.
Okay. All right.
But one of our friends had that exact scenario when it was very cold last week. And she messaged me and asked, how come the gasoline in my car is not frozen? And I was like, this is a very fun question.
Definitely fun question.
And a great episode for Chemistry for Your Life. So let's get into it.
Let's do it.
Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
All right. So I promised an episode on red food dye and the FDA last time we met.
But then we received a series of threats.
No. No. I received this text message asking me this question, and I thought, that is a really fun chemistry episode for the winter.
Right.
And the winter is almost over. And we did two kind of like behind the scenes chemistry, not like about chemistry information, but like FDA funding. And we didn't do any, straight chemistry lessons. And I thought that was kind of sad.
Yeah.
And so I thought it would be more fun to take a break and do this little chemistry lesson to celebrate the end of winter, the coming of spring, and answer Nicole's question. And I think it's a good one.
Mm-hmm.
So let's get into it.
Let's do it.
Okay.
I will say one thing I've heard that I don't know if this is going to come up at all, but I guess I haven't thought about, when you asked me earlier, I was honest, I have not thought about gasoline freezing. One thing I have heard about gasoline that would be curious if this comes up is that when it gets old, it can get clumpy. Like it has a shelf life, and after a certain amount of time, it gets all like weird and clumpy. And then it wouldn't flow well in a gas tank.
I have heard that, but I don't know if that's true. So I can look into it though.
Okay, cool. Follow up. Yeah.
Okay. But for this one, the gas freezing thing, I will say that I think you might be able to process through this on your own. Okay.
Okay.
And so I want you to think about, do you remember what happens when, just think of like one substance like water or something goes from solid to liquid to gas? What's happening on the molecular level?
Yes. So let's start with liquid because that's where we're starting with the gasoline, but pretend it's water, like you said. The molecules, all the molecules of H2O are when they're in liquid form, they are able to move past each other, in and out of each other at that temperature, but they're not so crazy spread out all over the place, but they are having the ability to kind of slide past each other with relative ease.
Yeah.
And that's because of the temperature they're at directly relates to the energy that these molecules are moving about in, right? And how much they want to move because of that. And so as we drop the temperature, the molecules are not moving as much. Their amount of energy or whatever is not as much. And the atoms want to be closer together.
Right.
And have less, would you say like less ability to move around?
Because they have less energy.
Less energy. And then they eventually become basically locked in place when it gets low enough.
Yeah.
But like we've talked about, there's not like and now you're not allowed to.
Yeah.
It's like, even though we have a freezing point of things or like a melting point of things, it's not like they are required to start moving right then or stop moving right then or whatever.
It happens more easily when they start moving, as they typically will start moving at a specific temperature, but freezing
is the more gradual.
Yeah.
Right. And we've also talked about the crystallization kind of thing, that being a part of it, where there's certain patterns that atoms want to line up in certain formations if they have the opportunity to, and stuff like that. But with ice, I'm guessing that's not really what's happening. It's just as is.
Well, sometimes it happens, but it just depends. Actually, our friend Grant.
It would be, I guess, if... Okay, sorry, go ahead.
Oh, our friend Grant sent me a really pretty picture of ice that formed during the Arctic freeze of like a nice crystalline pattern. So water can sometimes take on crystalline forms.
The frosts and those kind of... Yeah, exactly, right.
But it has to be just like the exact right conditions. I thought that was a great explanation. One question I was going to ask, though, there's a piece that you didn't mention, is do you know why they are more attracted to each other or less attracted and can move around?
In the case of water.
And I'll say for our listeners at home, can you think in your mind what's the thing that's making them want to stick closer together?
Use your imagination brains. And well, water is polar.
Yeah.
And so it wants to start to kind of get close together and interlock in the negative area is happy to be around positive areas, and positive, happy around, that kind of thing. But they don't want to be around each other.
What's that called?
Oh, which kind of polarity?
No, not what kind of polarity. What is the thing you just described the name for it? You described it perfectly.
Intermolecular forces. Sorry. I was like, I thought polarity, like polar and non-polar is already what we're talking about. I see. Sorry, the broader. Yep.
Okay, that was great.
Intermolecular forces, which, by the way, this might be a good time to just hint at the fact that we may have an intermolecular forces, a very new, very cool intermolecular forces merch piece coming this spring.
Wow, that's so perfect, because I did not plan for that whenever I made this.
I've been thinking about when should we drop that and like hint about it, because it's just been sitting
waiting. It is very cool. It is very cool. Okay, so I'm going to do a quick recap of everything you just said, but I'm so proud of how much you got. So now you don't have to do a recap at the end because you just did it.
Cool.
Okay, so what Jam was saying is true. I like to start the other way, from solid and then to liquid and then to gas, because for me, that is like very consistently you get a melting point. You don't consistently get a freezing point. So it's easier to think of it from solid to liquid. But when you have when you have a substance that's frozen, that is a solid, like Jam said, its molecules are kind of stuck in place. Now they are moving. They're like vibrating and rotating. They have a little bit of movement unless there's at 0 Kelvin, which means there's no energy in them at all, and they're perfectly frozen in space. But for the most part, they're moving a little. And so the individuals are moving, but they're not trading places with each other. So it's not flowing. They're like pretty well trapped in place. They might migrate a little over time, but not a lot. And then if you put energy into them, the more and more energy you put into them, the temperature will start to rise. They have more energy, and eventually, like you said, they'll get to the point where they have enough energy. And what's happening is they're overcoming these intermolecular forces. So the forces that attract them to one another are we'll say a certain level of strong. And once they get enough energy to break those forces and overcome those bonds, or those not bonds, but attractions, that's when it moves to like, okay, now we have enough energy that we can like sort of slide around. And then you put a little more energy and a little more energy, a little more energy. And ultimately, the intermolecular forces, the attractive forces between two atoms or two molecules, get totally overwhelmed. So I was trying to think about a good analogy for that. That's like, maybe it's sort of like a Red Rover situation, or like maybe like someone's holding you really tight and you start wiggling around, and then you wiggle enough to like sort of break away, and then they just only have you by the arm. Like, you know, when your sibling, have you ever had your sibling get you in like a headlock?
Yes. Well, I would say I was usually the one headlocking.
Oh, because you're the oldest.
Not the oldest, but I was.
Oh, that's right.
My older brother wasn't really. He's
not the headlocking kind.
No, he's not.
Yeah. Now I'm thinking that makes sense.
Yeah.
One time my sister headlocked me and walked me into a grocery store in public when I was in high school. Like, I could have run into someone I knew.
Right.
So think about that. Your sibling, you don't have enough, like, you don't have the strength to break away, but you might get a little bit free, and then but they still have a hold on you, maybe like on your arm. Mm-hmm. And so then you're moving more, but you're not completely free of them. Mm-hmm. And then you get enough energy to break away completely, and you just go totally away from them. That force of like your sibling holding you tight, that's the intermolecular forces. Okay. Is like, and if there's not enough energy to break free, they're just going to be held tight together. Mm-hmm. And the reason that those molecules are attracted to one another is because of the natural distribution of electrons, which is what Jan was referring to when he talked about polarity. So some molecules the electrons are evenly distributed across. In some molecules, there's like areas where there's a certain atom that is like selfish. It wants more of the electrons. And so it pulls electrons towards itself. And so then it is a little bit negative and the other side is positive. And then if it finds one of its friends, another molecule just like it, the negative side will be attracted to the positive side of the other molecule. And then so on and so forth, they'll keep attracting each other that way. And so they'll come close together. Now, that is called a dipole-dipole intermolecular force. And a really strong version of that is between hydrogen and really electronegative atoms, which are ones that like to take the electron density away, like oxygen. So water has that. But then there's, on the other side of dipole, there's something called dispersion forces, which is more of a temporary induced dipole, is what we say. So similar to tube magnets, like when they come close to each other and they repel one another, if you have two nonpolar electrons perfectly shared around them atoms, as they draw closer to each other, the negativity in one will repel the electrons in the other. Like just the fact that the two electrons are getting close together, it'll repel like it would a magnet. Mm-hmm. And so just for a brief moment while they're together, then that positive side, as the two come close together, they'll have like a temporary interaction and then they kind of move on. Mm-hmm. So those forces are pretty weak. So if that's the only thing you have and your molecules are not polar, it's pretty easy to overcome those forces. So if you have something like, we'll say, an oil or gasoline, which is made up of a lot of different just chains of carbons and hydrogens that are completely not polar, it is so easy to overcome those intermolecular forces that it can be done well below freezing, because you don't need a lot of energy to overcome those. And so you could be at maybe, for example, negative 50 degrees Celsius, and that's enough energy that your gasoline would start to melt.
Wow.
So it's just, you just don't need a lot to overcome those pretty weak forces.
Right.
And so because of that, our melting point of gasoline is much, much lower than our melting point of water, which has not only dipole, but really strong dipole forces that we call hydrogen bonding. Mm-hmm. So to make it very, very simple, all that to say, the state of matter that something is in, solid, liquid, or gas, at different temperatures is based on the intermolecular forces. So is it strong or weak intermolecular forces? Weaker intermolecular forces, you put more energy in, and they're easier to overcome those attractive forces. That happens at a much lower transition from solid to liquid, and then liquid to gas even. So some really low molecular weight, like methane. The reason methane is a gas at room temperature is because it has really weak intermolecular forces. But the reason water is not a gas at room temperature is because it has really strong intermolecular forces. So room temperature is not enough to overcome those attractive forces between each other. So
interesting.
So all that to say, that is why gasoline is a liquid at room temperature, and why gasoline is a liquid even below room temperature. But there's another thing going on besides just intermolecular forces with gasoline.
Okay.
And that is when we have impure substances.
Okay.
When we have something else mixed in, the freezing point or melting point lowers, which we've talked about before. When you put like salt on a road to keep it from freezing over, those impurities can basically interrupt the intermolecular forces in a way that makes them even lower. And gasoline is not just one pure thing. It's a mixture of things, including a lot of different hydrocarbons, which are nonpolar chains. And that mixture means that they're not going to just freeze at one particular point. And so you're going to get a broad range of melting, and you're going to get a depression of the melting point. It's going to go down.
Wow. Can I ask you this?
Yeah.
What if you mixed gasoline and water? Would it raise the freezing point of gasoline?
That's a good point. I think it depends. I'm not 100% sure. But I think it depends on what the majority thing is. So if it's like mostly water and you put some gasoline in it, I think your starting point is water, and water would come down. But if it's mostly like octane and you put some water in the octane, I think your freezing point would come up. And now I have heard, and I don't know if this is true, okay, because I don't live where this is, but I have heard that if you have a low amount of gas and then the temperature starts to drop, if like the amount of moisture that's just in your gas tank, because it's in the air, could start to mess with it and make it freeze. But I don't know if that's true. I don't know if that's true. I saw it in one place and I did not have time to look it up. But I could see that if it's like, yeah, I could see if you have like barely any, that could kind of mess with it. And somebody else talked about how when the temperature drops, the amount of gas they have in their tank changes. And that makes sense to me because as the intermolecular forces are, like, as we're taking energy away, they're being able to come closer and closer together. So colder liquid would take up less mass than larger liquid, which we talked about when my sister came on thermal expansion.
Yeah.
So.
Right. Wow. Yeah.
So we've talked about this concept before, but we've never talked about it specifically with gasoline.
Yeah.
And so I thought it would be fun to sort of revisit and have a quick little chemistry lesson. Get to talk about some oldies but goodies, intermolecular forces, polarity. That's like what we started the podcast. That's what we started the podcast talking about.
Yeah.
Was that? So a quick chemistry lesson, but you kind of already got it. So yeah.
And fascinating. Like, I don't know why I hadn't really thought about it. I guess there's a level of which I kind of just thought, I do know different things had different melting and freezing points and stuff or whatever.
Yeah.
But I wouldn't really have been able to tell you why gasoline specifically.
Yeah.
You know?
Or in general, why do things have different melting and freezing points?
Right. Yeah.
It's just because of intermolecular forces.
Dang, interesting. It would be kind of crazy if like we had landed on a really good fuel source for cars a long time ago. And it just so happened that fuel source definitely always froze. I'm just like, sorry guys. You just can't drive.
Yeah, after 32, like that's it. You just got to stay wherever you are.
Yeah.
It'd be sometimes.
Or it'd be like guys, go drip your car. Like you drip your faucets.
You know what? Other people don't drip their faucets.
I think part of that's because they're stuff's insulated.
Yeah,
better.
they live in places
Their
where
pipes
they
are
expect
actually-
it to get cold. Yeah. I've had some friends move here from cold places, and I'm like, wait, have you heard about dripping your pipes?
Mhm.
Do you know about that? Because you need to.
Barb didn't know about that, and she did that in Indiana, even though they had a lot more cold weather than we have.
Oh, okay.
So I think some of that may have depended on how, old different buildings were and stuff like that. But they were aware of it. She wasn't. I did wonder, like, is she gonna think we're so weird? She was like, oh no, we did that too. Like, and she was just renting somewhere. She was like, the last thing I wanted was my landlord getting mad at me because I like when my pipes froze or whatever. I was like, yeah, good point. It's like, even if your pipes are a little more insulated or something, they get colder weather for longer. It's like it probably still could maybe freeze.
Yeah.
So,
I had a friend who moved here from Nebraska, and I was like, have you heard about this? And she's like, definitely had to Google it, but yes, I have heard about it, and I'm doing it now. So that made me laugh.
That's funny.
All right. Well, that's it for today's episode. Is just a little bit of chemistry for your life. Just a little bit of intermolecular forces for your day.
How about this for a category to close out?
Oh, yes. Yeah. Let's hear it.
What's your favorite liquid that has a different melting point than water/ice?
My favorite liquid. Is yours going to be coffee?
I wasn't going to say that because I thought it'd be pretty close, right?
Well, yeah, but the impurities in the coffee would
Right.
would make it have a depression.
Okay, more different than...
More different. So water can't be the base.
I guess not. Yeah, or it's got to have a lot of something else in it.
What is a favorite liquid of mine?
I've got two really good options.
Okay, give them to me. That'll help jog my brain.
Olive oil.
Oh, yes. I do love olive oil. Yeah.
Or butter.
Yeah, well, you said what liquid, and now that I'm thinking about it, it doesn't have to be a liquid. It can be a solid.
Yeah, it just needs to be a substance that could be liquid.
Yeah.
Or solid that are different.
Chocolate.
Nice. That's good.
Like melting chocolate and having that melted hot chocolate as a beverage.
Totally.
Is good. Also ice cream.
Mm-hmm. Yeah.
Oh,
well,
yeah.
In that case, yeah. Huh.
Room temperature, it would be a liquid.
Yeah, that's true.
Has a very... Does milk have a different fruit? I guess milk is a high percent of water.
It's got more fat to it, which is why it's not a solid block when it's frozen. It's still creamy. Yeah. It's different enough, I'd say. I was thinking like things we interact with that we can interact with the liquid version or the solid version, depending on the scenario, that's different enough than water. But it is a very weird category to pick something from.
Yeah, but I do feel like ice cream is a good one because I interact with the solid version. Yeah, and it'll get you, and it can turn to liquid. And when we make ice cream, which we do sometimes, we make the liquid version of it. Well, we make frozen yogurt, so we blend up yogurt and then put it in our ice cream maker, and that's something we do a lot.
Yeah, we go the yogurt route too. It's like heavy on the yogurt side.
In butter, I do like when I'm making frosting. If it gets too hot, it really will get kind of melty. And also, I just thought of something, but then it went out of my brain.
Now I'm wondering what temperature olive oil would freeze.
I bet it'd be pretty low. If I had to guess, I think olive oil's freezing point would be pretty low.
I'm gonna guess 0 Fahrenheit.
Let's see, olive oil melting point. It says, this is just a quick Google. So who's to say? Melting point -6 Celsius, 21 Fahrenheit. You are very close, very very close. Yes.
Dang.
21 Fahrenheit, -6 Celsius.
Can you imagine like holding or maybe not holding because it would be so cold on your skin, inspecting an ice cube of olive oil? Like, what the heck?
Well, and I'll say this actually. You would expect butter to be a liquid at room temperature because it is non-fat, or it's just like hydrocarbon non-polar things. But because it's these long chains that are not branched at all, and they are they don't have any double bonds, so it's just like these. They make the same chevron pattern. They stack into each other really well, And so they form a solid more easily than you would expect.
Right.
And then also I think as the mass gets larger, like the size of something can impact its intermolecular forces as well. But we haven't talked about that very much. So, but with the size of something like a hydrocarbon chain that's short for gasoline, it's like octane. It's like, I think about the biggest. That is not going to have that much of an effect. So, and also gasoline is usually typically branched, which we talked about in our episode about how gasoline runs cars. So that was a good category. So comment and let us know, what's your favorite substance that can be a solid or a liquid that you interact with on a regular basis?
Yeah.
So it has a pretty different melting point.
Yeah.
Than water.
Yeah.
Also pasta sauce. It probably has a pretty different.
Oh, you know what? I have frozen pasta sauce before.
And I think people freeze olive oil they freeze it with like herbs in it.
Huh.
But your freezer just has to get cold enough, I guess.
Yeah, and I guess maybe, interesting. I don't think mine gets cold enough. I think mine gets to 0 Fahrenheit. So it was not close enough.
Wait, no, yeah, because it's 21 Fahrenheit.
-21, right?
No, 21 Fahrenheit.
Oh, so it can.
I think so.
Okay, sorry, I missed that earlier.
So you can freeze it.
Did you say -6?
-6 Celsius, yeah.
I see. That's why I messed
up. So you can freeze olive oil with herbs in it. I've seen people do it on the internet, and then store your herbs in olive oil.
That's cool. Yeah, I think because you said -6 Celsius, and then when you said 21 Fahrenheit, I just like in
automatically
my head, for some reason
distributed the negative. Yeah,
I don't know why.
So you can interact with a block of frozen olive oil.
Wow, cool.
Are you gonna do it?
I don't know.
That'd be kind of a fun experiment.
Yeah, it would be. I guess if I have a good container for it, I will. Like if I had a good little I don't just want to put it in a regular ice cube tray. We have these ones for these big ice cubes that I do for like cold brew and stuff. But I want to put it in something else that I'm not worried about.
Yeah.
Like getting oily or something.
So Mason, just like our roommate had these and he kind of adopted them, these ice cube trays. It's a silicone ice cube tray, but it's shaped like different spaceships from Star Wars.
Oh, nice.
And so whenever he's making salsa, he'll like roast peppers and just keep frozen cubes of roasted peppers, and then whenever he's ready to make it, he makes it with a can of tomatoes.
Nice.
But the perfect size is that spaceship, and so he will make frozen peppers in the Star Wars spaceship sizes.
Nice.
So
I love that.
You could use that for your olive oil cube.
That's awesome.
Make it an olive oil spaceship.
Yeah, that'd look pretty cool.
That would be pretty cool. I like that idea.
Well, thank you. Who did you say asked us?
Actually, this was Nicole, friend of the show and friend in person that we know IRL.
McCole. That's what my kids call her.
Oh, that's cute. McCole.
Well, McCole, thank you for your question. If you have a question, thought, idea, follow up to this one, correction, whatever, reach out to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts, ideas, and questions. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can join our super cool Chem community of patrons on patreon.com/chemforyourlife. You get cool perks, ways of us saying thank you, ad-free feed of the show, monthly virtual coffee hours for some of the tiers, behind the scenes kind of stuff, blah, blah, blah. Great way for us to just say thank you, because you are helping keep the show going and helping it stay free for everybody. If you're not able to do that, though, if you're not able to join our Chem community of patrons, you can still help us by subscribing on your favorite podcast app, rating, writing a review on Apple Podcasts or Spotify, and subscribing on YouTube and leaving a comment. We've been having a bunch more comments over there lately.
Yeah, that's been really fun. It's been fun to see those. Yeah.
We're closing in on 2,000 subscribers over there, too.
Oh, that's fun.
Very close.
Yeah.
So subscribe. And those things help us to share chemistry with more people, help more people discover the show and have the chemistry of their everyday life explained to them.
Well, this episode of Chemistry for Your Life was created by me and Jam Robinson is our producer. And like he said, this episode was made possible by everyone over at Patreon who supports us and makes it feasible for us to keep going on this podcast day in and day out. So we want to thank every one of those supporters by name. So we'd like to thank Julie S, Heather R, Autoclave, Chelsea M, Dorien V, Scott B, Jessie R, Ciara L, John T, Jeannette N, Cullyn R, Erica B, Elizabeth P, Sarah M, Rachel R, Letila, Katrina B, Suzanne P, Venus R, Lyn S, Jacob T, Brian K, Emerson W, Katrina G, Timothy P, Stephen B, Chris S, Chris and Claire S, actually, Chelsea B, Avishai B, and Hunter R. Thank you all for everything you do and for all your support to make Chemistry for Your Life possible. And I was about to jump my line because you were going to talk about references first.
Yes. Are you done?
Yep.
Okay. If you'd like to know more about today's chemistry lesson, you can check out the references for this episode in our show notes or in the description of the video on YouTube.
Yay, chemistry!
Yay, chemistry! Yay, gasoline!